Actions.
Group actions.
Exactly. What are they?
Actions on a group.
No.
Actions in a group. Actions of a group.
Yes.
Are we recording?
Yes.
Can you start again?
Probably. Actions of a group. So G is a group. X is a set. I think the book is quite consistent in this notation. So G is a group, X is a set. Except sometimes X is equal to G, which is confusing. But in general, you have any odd set and a group G. And the thing is called a left action of G on X. If it is a mapping, which as its domain has the it's called Cartesian product of G and X. So to every pair of a group element and a set element, it assigns a set element, like a GX. It assigns an element which is known as GX. That's the most confusing part of it. Okay, this is not the group multiplication because X is not from the group, but it's just done like that. Which has to satisfy two conditions. The first condition is that if you take the identity and act on anything in that set, what do you think you get? X. Yeah. And the second thing is, if you take a product of two elements of the group and you act on an element of X, okay, what you get is the same as if you only acted on X by the second element, G2, and then on which, so this will be in X, so you can act again by G1 or any. These are the G's are in G and X is in X. Okay. Not making any sense? Probably not before you see the first example or the second example also.
Students do want to see concrete examples.
Yeah, it's just the level of concreteness that we don't agree on. Okay. So example is provided. That's 14.1 in the book. So in that case, the group is the general linear group of 2 by 2 real matrices. Okay. And it wants to act on two-dimensional vectors in the real space or points in the plane. Any questions about this action? So you don't know how it acts, right? So if you get a point, which is so A, what are the elements of the general linear groups? 2 by 2 matrices in vertical. And X is just a two-dimensional vector, or you can think of it as a point in the plane. Well, then the action is multiply the vector by the matrix. Okay. Does that satisfy the conditions? So number one, if you take, well, the identity in the group is just the identity matrix. So if you do the identity times any x1, x2, what you get, well, x1, x2. So the first condition is satisfied. And the second one, saying that a bx is the same. So if you do a matrix times a vector and then times it by another matrix, you get the same thing as if you multiply the matrices together first and then times that vector. Okay, which presumably you know from your linear algebra first year that it works like that. I hope so. Okay. So do you remember when I told you, perhaps in my first lecture here, that you should think of groups as things that move something around? Yeah. Now we're coming back to that point. Yeah? We have a group of matrices and they move points around in the plane. Because you have a point, we have a two-dimensional vector, which is just a point in the plane. You apply a matrix on it. It's sort of it's called a linear transformation. You should probably know that geometry of it from linear algebra, even though I'm not entirely sure that Steve emphasizes that particular point of view very much. Okay, why are they called? So this kind of, why is it called a linear group? So it's a general. And this action kind of explains the meaning of the word linear. Do you know why? No? So Steve probably didn't do it. But so the linear, it was like the word linear is based on the word line. So if you get a straight line, let's say y, which is a subset of the plane, okay? So and then you take a matrix and then what happens is if you look at all the images of the points on that line, yeah, so I'm taking all the points on that straight line, timesing them by the same matrix A. You get a straight line again. That's why it's called linear. Which also brings me to another point that is not stressed in the book, is that you can have the same group acting on various different sets in a quite a logical kind of way. So for example, if you took, what's the next letter? Z. Take all the straight lines in the plane, okay, then G acts on Z in a natural way. Does that need explanation or is that clear? Explanation? Clear? Both at the same time? It's a bit like the Brexit debate. We don't want to leave, we don't want to stay, we don't want. Nobody knows what they want. No. So if you get a straight line, any one straight line, you look at each point separately and see where the matrix maps it. And that gives you a new straight line. So this is the image under that action on the set of all straight lines. Okay. It also acts on the set of all triangles and many other things. Okay. There's another example, which is 14.2. What's D4?
Symmetry group of square. I just read
What does it say there? The symmetric group of a square. Yes, it is. That is true. Yes, yes. So D4 can act on the square. What is the square?
Sounds weird when you say it.
What is the square?
The four-sided shape.
So, for example, this. Yeah, so a subset of the plane, we just take the interval from -1 to 1 horizontally and -1 to 1 vertically, and all the points in that square for the square. But that's not what we usually thought of when we were talking about it. Because we were writing the dihedral group as a subset of the symmetric group, and it was just acting on 1, 2, 3, 4. So that's different action, kind of. So 2, the vertices of a square. So in that case, we usually say it was 1, 2, 3, 4 the set that was acting. Where does 1 go? Where does 2 go? Many applications of group theory to various things. It's quite useful to think of the actions of the same group on different but related objects or different or related sets, just like here. So the square and the vertices of the square. So it's easier to study the group D4 itself when you just think of it as permutations of 1, 2, 3, 4. But maybe sometimes if you're doing the geometry of a square, like the actual symmetries of the square, then you're actually thinking of it as the group of symmetries of the geometric shape. And the kind of interplay between these two points of view can give you some interesting results.
It's passing your first page.
Now people are still looking at it.
Then you finish.
So if you take the element, we had these two conditions, or usually, like, I'm still looking at it myself, we had these two conditions in the definition, which talk about the identity and kind of associativity in some sense. But there's no mention of the inverse in the group. So if you have an element of the group G that maps X to something, then you would expect the inverse of that element to move it back. Does it really do it? Well, you can put Gx for Y, because that's the assumption. And then using condition 2, you get that this is G inverse G X, which is EX, which is X. So it indeed gets you with that. So note applied to the first example of the general linear group was that if A kind of moves X to Y, then the inverse of A moves Y to X. So in other words, if you do the inverse of A applied to AX, then you get X. What was that for? Did I say anything wrong? And that's how it works all the time. Okay. What's next in the book? There's this bit at the end of page 223. In general, if X is any set in the subgroup, so kind of trivial. So if G is a subgroup of Sx, Sx is the set of all permutations of some set X, then G acts on X. Okay. Right. Obviously, because a permutation is already a mapping that satisfies these conditions. So, silly thing, I don't think but also on pairs, which means on X squared, so on. The book doesn't write it, but it's more important, more interesting than just what it writes. What's 14.3? Oh. So the group acts on itself. So a group G acts on X, which is also G, something we called I don't know. So if you get an element of the group and another element of the group, what you get is this lambda gx, which is gx, okay, or g times x. Kind of confusing now because the notation is gx and gx is the same thing, but it actually turns out to be the same thing. Yeah, this lambda g, do you remember we talked about, it was one of the submission problems, which was to prove that it's a permutation for every g of the group.
It's not an arrow. GX goes to lambda.
Yeah, that's an arrow with a... Hopefully Killian explained the difference between the arrow with the thing and without the thing. Well, then you have to ask him again. Okay. So if you get the pair G from the group G and X from the set X, which also happens to be the group G in this case, then this is assigned the product G times X in this group. It's an action. To confuse things further, we get action by conjugation. So this is again, G acts on, no. Okay. So when you get some G and some X, this thing gives you GX, G inverse. This is very rarely denoted GX because GX is something else. So we don't know that now. But also it can be so it doesn't have to be the whole group acting on itself by conjugation, but it can be just a subgroup. So then right, the mapping itself is written in the same way. So in this case, these H's have a smaller domain than these X's, but it's the same kind of thing. Does the book expand on that in any way? Oh yeah, it checks that it actually is an action. So it checks that if you do if for H, so the first condition was that EX, E inverse has to be equal to X, which it is clearly. Yeah, this is just group multiplication here. And the second one was that when you do H1, H2, X inverse, what you should get is what? So this is what this pair is assigned. Okay. And this should be the same as if you do H1 on not H2X, but H2X, H2 inverse.
What do you mean this is what that is the sign? Why is it that?
Well, I mean that if you have, so this is not 1, this is a comma. Okay. So if you have a pair, any element of the subgroup and any element of the group, the action is a mapping which takes the pair and assigns this product in the group, which is an element of the group as well. Okay, element of G. So if you take a pair where the first one is a product of 2 little h's, each of them from H, big H, then what you get is, by the recipe, that element times the inverse of that. And by the second condition, what you get from here should be the same as what you get from there. Because this is what you get from H2 and X. And from this, what you get is H1, H2, X, H2, inverse, H1 inverse. Oh, I fucked up. I left too much space, but actually it's, you don't have to write any intermediate results because you can see that they're equal. Hopefully. Is that clear now? But you missed the definition. It's not clear. And so this gives us 2 different ways in which the group moves the elements of itself in ways that are going to be important for what we're going to do next. Because what we're going to do next is the class equation. Who's doing the counting the number of ways how to color a triangle?
Number of colors is from.
Yeah, so we're coming to her project. If she waited until now, like next week or so, she wouldn't have to do any work anymore. It will all be done in the lecture for her.
I tried the same thing, but skip my job.
Really?
Chapter 12 on symmetries. I didn't actually try it. I did do more work, honestly.
You don't know.
Good.
Only 50 people.
Okay, 14.5, I'll just mention it. What does 14.5 say in the book? G acts on what they call LG, is that right? L. Why? Oh, yeah, LH. So this is the set of all left cosets of some subgroup H. So again, if you get an element of G and the left coset, which is HG, well, it wouldn't make sense to assign anything else than the coset of the product GH. So this is exactly where we differ on the level of concreteness. So this is a very concrete example to me.
And when we've all got our doctorates, we'll come back and agree with
Okay. Now we're coming to orbits. So let G act on X, so we have an action, any action. Okay? And two elements from the set that is being acted upon are called G equivalent if you can move one onto the other by acting. So if there exists something in the group which moves X to Y, and they're called equivalent. G equivalent. What is that good for? For orbits. That thing. What does Killing call it? Boom. Tilde.
Tilda.
No, he has a special word for it. Called something like swoom or whoop. No, I can't remember. Yeah, it's a tilde indexed by G.
Index by G.
Yes.
What does that mean?
G equivalent.
I just defined it. Okay, so you have a group. The group, what it does is it shifts the elements of some set around. Like, for example, the elements of points in a square by rotating the square and flipping it. Okay? And 2 points are equivalent if you can do something with the square that the group does to it and get from one point to the other. Okay, so for example, if you take this point and that point, which even though it doesn't look like it, but they have the same distance from the sides of the square, then the group element which reflects the square by the what's it called, the vertical axis moves this X to this Y, and therefore X and Y would be G equivalent or D4 equivalent in this case. Okay, that's a very concrete example. I can't think of anything. Okay, is that all right now? Or another example, or we'll have more examples. Well, another example is when you have well, we didn't really do the rotations. So then, if you have, like, I'm not saying which group it is, we're talking about, but if you have 2 points, X and Y, that lie on the same, about the origin, that lie on the same circle centered in the origin, then you can find their rotation that moves one onto the other. But if they're not on the same circle, you have Y dashed, which is far away, then you can't move X to Y dashed by a rotation around the origin. Okay? And in the same way, you can't move this X to this corner, for example. So there's no way you can do a symmetry of the square that moves a point in the middle into that vertex. So they're not G equivalent. Okay? Why is it called equivalent? Because it's an equivalence relation. Where are we? 46 already. It's going nicely. So, I think everything here, every definition, theorem, proposition, and lemma starts let G act on X. Then the G equivalent is an equivalence relation. On that set. What does it mean to be an equivalent relation?
It's positive,
Okay.
reflexive. Yeah, that one. Good job I'm not doing a project on the
Okay, transitive, what does that mean?
if X is equivalent to Y and Y is equivalent to Z, X is equivalent to Z.
Okay. That's true. So now we're trying to prove that X and Z are also equivalent. Well, the definition of the equivalence relation was that there exists some G that moves X to Y, and there exists some H that moves Y to Z. Okay, but then this GH moves X to, by definition, sorry, by the definition of action, so the second point says that you can move the brackets like this. And, HX is Y and GY is Z. So also we found something that moves X to Z, so X is G equivalent with Z. Reflexive because E moves X to X, so X is G equivalent with X. And what does symmetric mean? Symmetric means that
Y.
yeah, so we're trying to prove that it goes backwards. It's not like a it's not symmetric. So this means that there exists some element of G, okay, which moves X to Y. But then as I said 20 minutes ago, the inverse of G moves Y to X. That's the end of the proof. Now, a slightly funny definition. It starts in the traditional way, so let G act max. An orbit of X under G is any equivalence class of the G equivalence. Well, and the orbit that contains X, little x, is OX and is called the orbit of X. Okay, maybe I'm getting too detailed here. Right? So that's nice because there are plenty of exercises on finding the orbits of different groups acting on different sets in the book, which we're going to go through in the tutorial. But as some examples, so for example, what kind of actions do we have as very concrete examples? I've lost the sheet somewhere. Where's my first sheet?
Yeah.
Oh. What was on it? A general linear group. That's kind of boring. Okay, example. So when we had the general linear group acting on the plane, what are the orbits? So, for example, if I give you 2 points like 3, 1 and 4, 5, can you find me an invertible matrix that moves, that when you take in multiply 3, 1 with it, you get 4, 5? And 1, 1, 2 will do? Okay. So that was easy, but can you move any point in the plane to any other point in the plane? Yeah, no. Both answers are correct.
Are there?
How can they be? They can't be. So, yeah. Pretty much, except except 0, 0. You can't move anywhere else than 0, 0. And at the same time, you can't move anything else back to 0, 0 because you'd need a singular matrix to do that. It comes from linear algebra again, and referring back to things you should know. So yeah. Is it time to go? Oh, it's time to go. How sad. Yeah, but it's true because so you know, kind of. Yeah. Yes. So the orbits. So there are two orbits. The first orbit only contains the 0, 0, and the other is the remaining point. And now apparently it's time to go, so. So go then.
Spread the word.